Well, howdy. I'd like to try this example on my tablet, see if these work out a little bit better than on that screen. Doesn't really matter for now. I'm pretty much stuck with the tablet, unless Dr. Moser sort of calls me and says I've been made essential personnel. So we've got a shark, right, doing sharky things. Oops. This is not the best shark. I have, in fact, drawn better sharks, and that goes off the screen. Okay, so I need to practice drawing on the tablet anyway. Needs an eye and a smile. And so he's running around. He's cruising, moving along at 50 kilometers per hour. And as he's going, he sees a little fishy. Minding his own business. He says he wants to stop, turn around, and get lunch. Put the little fishy in a brown paper bag. And so the question is how far is this distance that he's trying to stop, right? So he wants to figure out how far it is he's going to stop. All right, so, yeah, let's call that X. You want to find X, right? Call that X. So what do we know about this? We know that the shark is heavy and that we've got some drag going on. So when the shark turns, right, the thing that's slowing him down is not going to be like friction from the ground. So that's what usually slows you down when you're walking, right? When you want to stop, friction has to do it. You've got different ways to do that. You can slowly do it with each step, or you can try to do it all at once and probably do a face plant, or maybe you can slide or something like that. But the shark doesn't have that. There seems to be absolutely no ground in the middle of the ocean, or at least anywhere nearby. It's pretty far below. So the shark needs to use drag. So we're going to pretend it's viscous drag, probably in this case, because he's going to turn, this way while he's trying to slow down, right? He's not going to keep on going in the nice streamlined state that he has here. Probably would be quadratic drag, but this will make it easier. So this is less aerodynamic, so you get a higher drag constant, which means you stop quicker. If he just stopped swimming with his fin there, then he'd slow down as well, but he'd slow down a farther distance. Call that one D. So what we want to do is we want to figure out how much that slowing happens, how much all that water, basically hitting the shark and going over it reduces his speed, or how far it takes for him to slow down. Oh, thank you. Please don't email me while I'm doing this. I'll remember to mute that. I usually have everything on mute, but these are different times, right? So, let's see. What does this mean, sort of, in terms of the physics? We said that we have a shark, and here is a better version of a shark. Okay, so that's how I draw a shark, as a box. And then we're going to give the shark some axes so we know which way is which. So we'll call this direction over here Y and this direction over here Z. And then we'll have to figure out what's going on with the shark. So what sort of things are affecting the shark? Well, he's a heavy shark, so obviously there should be some weight coming down this way. But he's not falling. Right, so he's got a weight coming down this way, but he's not falling, so he's got something pulling him up here, and that's going to be called buoyancy. So we'll put the buoyancy that's keeping him afloat there. And then we've got some drag pulling him backwards. right? Got drag coming over here. So I don't know exactly how I want to do that. Let's make a really big one, D. And then we need to figure out what else. So there shouldn't be anything else, right? If he was swimming, there'd be a force coming this other direction, right? But he's not swimming because his whole idea is to stop swimming so he can turn around, right? So he wants to turn around, therefore he stopped swimming. There's no force. He's not adding any propulsive force in the positive y direction. And he's slowing down, and that means he has an acceleration going backwards. Okay. So that tells us what the physics looks sort of like. Next thing we want to do is we want to figure out how far he's going to go. So I just sort of gave you an equation for that. I told you that there was an exponential decrease. So if I was to draw, okay, let's say 0 here is this point where he starts slowing down, and this is time, and this is position. We said that as he starts slowing down, there's going to be some limiting value here that he exponentially approaches, right? Something like that. So he's going to start slowing down really fast, and then he's going to start slowing down slower, and after a little while he'll be able to just use his fin and turn around nice and easily. So the question is what is this value, right? And I gave you an equation that was x of t equals v naught over alpha times 1 minus e to the minus alpha t. This alpha is sort of this decay constant. That's how fast this approaches, how fast he approaches this limiting value. And so we have to know something about that. And v naught is the original speed. That would be the 50 kilometers per hour. All right, so this guy here is 50 kilometers per hour. This guy we don't know, but the question is do we have enough information to find that? Well, luckily I also told you what alpha was, right? And alpha was C1 for your viscous drag over M. Just that simple. So part of the reason why I'm doing this with linear drag is you have this nice simple equation. I don't remember. It's a lot uglier, but it's not as advanced. It's sort of weird if you do it for the quadratic drag. But I didn't really feel like throwing all that many equations at you. Although I did want you to know that you do stop at a point, right? So we're looking at this, and it turns out that you never actually get to this point, but you get really, really close. There is a limiting value. And that's happening while your speed is reducing. So your speed is doing this, and your speed never gets down to 0 either. So you never stop moving, but there still is a limiting value. There is a distance that you actually go. And so I wanted to get that point across, which is, again, yes, you never stop moving. Zeno's absolutely correct, right? You never get to 0 velocity, and you never get to this v naught over alpha, this limiting distance, unless you do a little bit of something else, and that could be just random fluctuations. But in fact, you do not go on for infinity. You don't keep getting farther away, even though your velocity never actually gets to 0. You don't have an unlimited range just because the velocity goes to 0. Because the velocity keeps decreasing, you have a limited range still. And you get to very, very close to that limited range in a reasonably short amount of time. Okay, so that was the reason for putting those in the lecture. And now I've got a bunch of crazy stuff with lines all over the place. So it appears that we need to get this part. This is going to be what our x is. So our x is going to be the v naught over alpha. but we're going to have to substitute that alpha in there. So that's going to be the mass, since it's 1 over alpha. 1 over alpha is just the opposite of alpha, right? Instead of C1 over M, it's M over C1. So we have M times V naught over C1. Okay, and with that, I'm going to be able to actually put some numbers in and solve the problem, right? So this is where we are now. See, this is the big advantage of using the tablet, is that after I have all this wonderful, wonderful math here, isn't that beautiful? I can sort of summarize it in a nice, clean way and go on to the next part of the problem and still have plenty of room. So let's see, what do I want to do now? I want to find that x. I want to find this guy, right? So I have x is equal to m over v naught over c1. And I happen to have all those values. I have a 200 kilogram shark. And I have him going at 50 kilometers per hour. And I have a 200 kilogram per second damping drag constant, not damping constant. First thing I notice is I've got two 200, so I can get rid of those. I can also get rid of the kilograms. That means I have 50 kilometers seconds per hour. Okay, so that's not so good. So we want to get rid of those seconds per hour. So if we have seconds in up top and hours in the bottom, that means I need 1 hour and 3,600 seconds. All right. And then we have 1,000 meters in a kilometer. I don't know if we really need to do that. I guess we probably do. Okay, and I can get rid of a couple more zeros, right? So then I have something like 50 times 10, so 500 divided by 36. Okay, so we have 500 divided by 36. Hours cancel, seconds cancel, kilometers cancel, meters. So 500 divided by 36 meters. And so that is 1, right? So 500 minus 360, that leaves me with 140. We have 140 divided by 36. So I'm going to guess 3 times. I think we probably won't be able to get 4 in there quite. So let's see, 3. And let's give that a guess at 9 meters. So 13.9 meters. All right, so that would be the answer right there. Let's see how close I was. Oops. I have to swipe to move from screen to screen. You just saw it. Peek behind the curtain. I'm sorry. I ruined the mystique. So here we are. We've got the entire problem. First, I analyzed this equation that we had previously, right? This part here was our limiting distance. This part here, this guy was the definition of the damping constant, or dissipation rate. We'll just call it rate. This guy here was the actual reduction. So we took the limiting distance, which is what we cared about, and added in the definition for this alpha, which we weren't given, but we were given two things that were related to it, right? Put those together, so we got a little marginal equation there, tossed in all our fun numbers, and ended up with 13.9 meters. Reasonably reasonable, I'd expect, wouldn't you? So that is a pretty quick run through of something to do with damping. All right. I will talk to you in a few minutes my time. I have no idea how long it'll take for you to look at the next video. Bye now.